Okay, so now we already did the same problem using the method of the sections, the method of the integrals. Now let's work out the problem with the method of the areas. Method of the areas. The method of the areas, but you really need to pay attention to me when I'm doing this because it's really easy to get lost. It's a method that is so fast. A bunch of professors don't allow you to use it. I don't see why. Some professors say that the method doesn't work for every case, and that's a lie. The method always work. I don't, if you don't know how to use it, that's a different story. Now, what happens is that sometimes it's more difficult to use a method than to use the integrals, for example, which is not the majority of the cases, but sometimes it happens. So same problem, ABC, solve it. First step, calculate reactions. I already have the reactions. I'm not gonna waste time doing that. We already calculated those. Second step, discontinuities or interest points or points of interest. What are those points of interest? At the beginning, at the end, wherever you have a concentrated force, wherever you have a concentrated moment, wherever the distributed load begins, wherever the distributed load ends, wherever you have an internal support, wherever you have a hinge, wherever there is a change on the geometry of the section or the material, at least for mechanics of materials and solid mechanics. And those are the points of interest. What do you do with those points of interest? You just place vertical lines, which are going to be the boundaries for your diagram. If I had axial, this is a pin, and this is a roller. If I have axial, I would put another line to draw axial diagram, but I don't have any. So I'm gonna put the shear diagram here, the moment diagram here, and this is gonna be my baseline for each one of them. I like to put the units here, the units here, so I don't repeat the units every time. So method of the areas. Are you ready? That was yes or no, guys. Okay. Not that I don't care if you're not ready, but I don't care. But okay. What is the definition of area? Tell me. Talk to me. No. BH is not the definition of area. Or okay, what is the definition of the integral? Let me switch it back. Area under the curve. Correct. So we're gonna start this in the same way that we started the rest. We're gonna start point, span, point, span, and so on. So the first analysis that we're gonna do, and I'm talking about the shear, right? Shear. The first analysis that I'm going to do is that shear, point A. And then we ask ourselves that question, is there any concentrated shear at point A? Yes, it is. Oh, I don't see any. Of course you see it. The reaction, that is a concentrated shear acting there. Why is shear? Because it's perpendicular to the cross-sectional area, parallel to the cross-sectional area, perpendicular to the axis. So you have that shape over there. That means that this is gonna jump up my diagram. And I want you to do this when you solve it for me, okay? Because it's the only way that I'm gonna know if you really work it out. So it's gonna jump up, meaning from this point, it's gonna jump up and it's gonna go 133.75. Now, after that, we go to the span AB. The span AB starts with 133.75 with the shear. And then suddenly I find this force, which is 40, and this is pointing down, and this is 8. Because the integral is the area under the curve, then basically what we are doing when we do integration is calculating this area. but it's negative, you see, because the loads are going down. So what I have is 133.75 minus 40 times 8, and that's negative 186.25. Negative 186.25. Because this is constant, this is gonna be constant slope. First part, thunder. Now I go to the point B. My point B starts with 186.25 here. And then you ask, is there any concentrated shear force at point B? Yeah, of course, the reaction, which is this one, 206.25. So negative this plus this is gonna jump up to 20. That means that from here, this is gonna go up to 20. And then you go to the span BC, and then in the span BC here, do you see any shear load at the span BC? Is there any load in this span? So no load, that means that it's gonna be constant. So from here, it's gonna be constant up to that end. And then you go to the point C. I started with 20, and I found a concentrated load of 20 pointing down. That's gonna be 0. And then you say yes. What method do you like the most now? Of course. It will freak me out if you say sections. Okay, now let's go to the moment. Moment, give me a moment. The diagram goes into a bar, and the bartender asks, what can I give you? And the diagram says, give me a moment. This is so stupid. Okay, anyway, moment. Same thing, start, point A. Is there any concentrated moment at point A? Now, you can have a concentrated moment at point A, for example, if this is a fixed support. But if it's a pin, unless you have one moment applied, there's no concentrated moment. So it starts in 0. No concentrated moment starts in 0. So this is the first point, 0. And now, when you see this, is that you have to use a geometry approach in order to solve this, because you don't have the equations for doing this. We don't have the equation for doing this like in the previous cases that we went the shear 0, etc., etc., etc. So then that's when this thing becomes really user-friendly. 133.75, 186.25. Those are the values that we have over there. And this distance is x, and the total distance is 8. This is what we have. And this is what I was explaining you before, that you can relate, you can say x is as 133.75 as 186.25 is as this distance, a minus x. Or you can do what I do, which I think is easier. I just do this. Once you get a hold of it, it's really easy. And then you say, if these two lines are parallel, this is the same thing, right? 133.75. And you create a method if you want to. I don't want to memorize anything. So 133.75, and this is 186.25. And what I do here now is that I just compare, instead of comparing this triangle with this triangle, I compare this triangle with this triangle. with this triangle. And then I can say that x is at this angle. X is the tangent of this angle is what I'm comparing actually. 133.75 as 8 is as 186.25 plus 133.75. And then you solve for x, and your x is going to be equal to 3.4 something something something. We did it before, 3.4375. That's the value for x. And if you look closely, this is your equation. You see, x is the point that you're looking for. This is the value of the load of the triangle in this side. 8 is the total length, and this is the summation of both values, this value plus this value. And that's it. You can apply like that every time, and you don't have to do the drawing that I do. But I would love you to do that. So now we know that. We come back here, and we know this is 3.4375. And then we keep working with our moment. This is what we were doing with the moment. And now we start with 0, right? And we go to the span AB. Span AB. If you go to the span AB, this is a positive area. And I start with 0. So 0 plus the area of that triangle. 3.4375, 133.75. Meaning this is going to be 0 plus 133.75 times 3.4375 divided by 2. 133.75 times 3.375 divided by 2. And that's not the value because I did something obviously wrong. What is the value that I did wrong? I did something wrong here. What is wrong here? The value for x is wrong? I think the value for x is wrong. I don't know. I'm just doing this with the value that you gave me before. $3.34375. That's correct. Okay, then what am I doing wrong? The area of this is the value 133.74. You put 3.43. Oh, maybe. Oh. That's it. You're correct. This is 3.34375 times 133.75 divided by 2. And that's 223. Correct. Dyslexia. That's called dyslexia. And that's 223.61. That's the value of the area. Look how just a little decimal over there changed the values. So then I know that somehow this is positive and I'm going to end up here. So 223.61 right there. Now you come back to the circle. Please don't neglect infants, neglect dumb people instead. And you say positive because it's plotted above, increasing because decreasing because the absolute value of the function from left to right is decreasing, positive decreasing, positive decreasing. And then you get to that point. Now, you keep going, and then you go and you find 223.61. That's the value that we got. And you find this area, which is a negative area. And this area is, if this is 3.34375, then this is going to be 8 minus that. It's gonna be 4.656. 4.65625. That's the distance there. 4.65625, and this height is 186.25, and the whole thing is negative. So 223.61 minus this area divided by 2. That's 210. Negative 210. That means that I'm gonna reach this point here, negative 210. Once again, positive or negative? Negative. Why negative? Because it's plotted below the axis. Increasing or decreasing? The absolute value of the function is increasing. So that thing is negative increasing, negative increasing, negative increasing, negative increasing. Right there. There you go. Now we go to the point B. Is there any concentrated moment at point B? No concentrated moment, no change or no jump. That's it. That's all the work that I need you to do. Okay? No jump, no change, no nothing. Now go to BC. If you go to BC, what happened with BC? Well, I start with the value of negative 210, and then I find this area, which is a positive area, of 20 times 3. Negative 150. That means that from here, negative 150. Because this is constant, the slope here is going to be constant, so it's a straight line. And then you go to the point C, and you do the same thing. You have negative 150 here, and then I find this moment of 150, which if I look at the direction of the jump by looking at the left side, it's going to be negative 150 plus 150. This is 0, and it comes with your big yes. Just if we have any doubt. Yeah. Cool, right? And this I think is cool. Now, what do you do with those values? Well, you use these values for designing. For designing what? Watch my other videos, but for designing what? Well, the moment is used basically for bending for this part of the design. And the shear is used for cross-sectional area related when we try to cut it in that direction. Any questions? Questions? No more questions? Or no questions whatsoever? Am I alone? Nobody's watching me? 28! Oh my God, my audience came from 100 almost to 28. So boring, I'm so bored. Boring. Okay, guys, anyway, I'm just gonna put this thing online, the videos, and that's why maybe because they realized I was gonna put the videos, I said, just watch a video, that's it. And I don't know, I see you Tuesday, right? I think we have a meeting in person again on, well, in person, virtually in person on Tuesday. So see you next time, guys. Do you have any question for me before I close? So the diagrams are not gonna be part of the test. I say that only like 300,000 times, but in the final, yes. Uh, anything else? Okay, I'm gonna stop here. And